Hi there. Welcome to Labster. Here you will learn about the basic concepts of evolution and natural selection. We'll also look at other genetic selection processes to see how they differ. Just so you know, my lab assistant has created a minor emergency in another room and we'll need to take care of it before we start the lab. I'll take you through the tutorial first. This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch the play mode. If you disable the sound effects, the lab pad will slide up whenever there are instructions to read. You can select what type of audio you prefer. Deselecting any of the options will mute that option. Click Continue to learn how to navigate through your mission. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you've played a Labster simulation? Perfect, then let's get started with your first mission. By the way, how do you feel about dogs? Brilliant. You might be just the person I need. Forgive me if it's a little rowdy. Oh dear, here they go again. I'm embarrassed to ask for help, being an all-powerful AI, but I'm in something of a pickle. My lab technician is on holiday and asked if I could dog sit for them. I thought it would be easy. How do I make them stop? Oh, I've heard of this. Let's see if I can mimic the tone. Does that sound right? Oh sorry, I forgot you can't hear that high. Here goes. Thank goodness for that. I searched every publication on canine genetics and psychology for an answer, but none of it applied to this situation. Humans can be so useful. You seem to know something about dogs. Which dog in front of you do you think is a different species than the other dogs? You got me, that was a trick question. Despite being part of different breeds, these dogs are all the same species, Canis lupus familiaris. Common gray wolves are also part of this species, as domestic dogs and gray wolves can produce fertile offspring together. Dog breeds are the result of human-controlled selective breeding over the past 10,000 years. The same mechanism created modern corn cobs from corn ancestors with relatively few kernels per head. What do we call this trait-conserving process? That's right. Conversely, we call the process of incremental adaptation in the wild, natural selection. Random mutations can improve or reduce a creature's likelihood of passing their genes to the next generation. In artificial selection, an organism's genetic succession is actively controlled. Organisms carrying strong desirable traits like greater food production, efficiency, or perceived cuteness are allowed to proliferate. Dogs, wolves, and coyotes are all descendants of an ancient wolf-like species. Even further back in history, there's an ancestor that relates to foxes as well. The family tree is so interesting. Come to think of it, this fits nicely with what we're working on today. Let's figure out how we got to have so many different canids running around the planet. Now the pups are quiet, let's head back to the lab. It's time to move to the second room and take a look on the hollow table. Check it out, tiny canids. This hologram visualizes data from an ancient ancestral colony of early canids. Right now we're observing them at 1,750,000 years before the present. We monitored everything about the creatures, from their feeding habits to the genetic makeup of every member. As we're in a virtual lab, we can holographically model the colony and jump through time to visualize genetic impacts on the colony over millennia. Take a moment to explore the terrain for organisms. Explore the hollow terrain and find the canids. Raise your lab pad to continue. Did you find all the creatures? There are 6. The forest provides great camouflage. Let's call this ancestral colony of canids, Generation 0, or G0, for short. I've displayed some frequency data for a random gene on the floating console next to you. I'll call it Gene 3. You can see that each individual has 2 copies, or alleles, for each gene. That makes sense as gene-storing chromosomes come in pairs. One set comes from the mother and the other from the father. The gene is well conserved in this colony. How frequently each allele occurs in the canid population is displayed on the floating console. Usually, we express allele frequency as a percentage of the total number of alleles in a population. You can see gene 3 has two versions or alleles, denoted by the icons carrying one or two triangles. You can tell if wolves are homozygous or heterozygous by checking the alleles under their image. Lowering your lab pad will allow you to check the console data at any time. Over this mission, let's critique the random changes we see in the colony. I bet you can hypothesize the impact of different genetic alterations after a few rounds. Take a look at gene 3 allelic distribution data in the floating console. If we assume the canid colony has 1,200 members and all members are included in this data set, how many copies of the less common allele are present in the whole population? Right on. You remembered that each individual has two copies of the gene, so the total number of alleles in the whole colony is 2,400, not 1,200. 35% of 2,400 is 840, so we can assume that in this canid colony, the less common gene 3 allele appears 840 times, sometimes as a homozygous pair, other times heterozygously. Spin the gene wheel for a random genetic impact. No mutations. Well, that's unlikely to make much difference. Let's see if the population changes over time without any mutations. Trigger a time jump using the button on the hollow table and check for colony differences. The data console isn't showing any change in the gene 3 allele frequencies. Have you heard of something called the Hardy-Weinberg principle? I love your confidence. Let's check you've got the basics dialed in with a quick pop quiz. If you want to refresh your knowledge, you can always check the theory tab in your lab pad. According to Hardy-Weinberg theory, what would it mean if the distribution of allelic frequencies within a population shifted over time? Well critiqued. Hardy-Weinberg principle supports this idea. Allele frequency distribution would only stay constant in the complete absence of selective pressure. In reality, this situation rarely exists if at all. The environment and the organisms within it are constantly changing. Which reminds me, let's give the wheel a spin and see what gene mutates in our canids this time. Spin the wheel again to induce a random genetic impact. Now we're talking. You got gene 5. Let's check in on the animals and see what effect this mutation has. See if you can spot any differences in the terrain and on the console. I've updated the console with gene 5 data from both the ancestral G0 creatures and the genetically impacted colony we're currently looking at so we can compare them. Check out the canid colony on the hollow table and the data on the screen. Raise your lab pad to continue. Our spinner simulates the random nature of the mutation. Remember, mutations in nature aren't actively induced to make an individual better suited to its environment. Did you notice any changes in the current generation of canids? Genetic alteration occurs more often than you might think. In humans, each time DNA passes to a new generation, about 100 to 200 new mutations go with it. Most of the time, mutations are neutral or benign. Such changes have no impact on the form or function of the product the gene encodes. I'm not detecting any changes in canid behavior or ability, so it looks like the mutation in gene 5 is neutral too. What do you think will happen to the new allele after a few hundred rounds of random mating? Okay, let's jump through time and see what happens. Trigger another time jump to look for changes in the terrain and data console. It looks like the gene 5 mutation has been removed from the colony. This often happens to uncommon neutral variations. Where multiple neutral alleles of a gene exist, genetic drift generally results in one version becoming dominant and all others being lost. Let's spin that wheel one more time and induce another mutation in the canids. Spin the gene wheel to make a random genetic impact. Awesome, you got gene 9. Let's explore its impact on the colony. Check out the canids and their data. Raise your lab pad to continue. What did you discover about gene 9? Yes, you're right, a new gene 9 allele has appeared. From the data displayed on the console, it already has a 10% frequency in the colony, meaning it qualifies as a genetic polymorphism. There must be some advantage or evolutionary pressure that's keeping this allele around. Is there anything else you noticed or want to talk about? Yes, I noticed that too. There is a creature on the screen that is brown but appears to carry a single new variant allele. The ancestral brown allele must be the dominant one, while the new polymorphism is recessive. Two heterozygous canids could still produce a gray pup. Is there anything else you noticed or want to talk about? Sounds like you're getting the hang of this data modeling thing. Righto, let's look at the future canids. Before we jump, what do you think will happen to the new gene 9 allele in 50,000 years? Let's jump time and find out. Trigger a time jump using the button on the hollow table and check for colony differences. That's weird. We can see from the data console that the new allele is still present in the colony, but there are no gray canids in the colony. I wonder what's happened. Nice thinking. If the gene is following Hardy-Weinberg distribution, we would expect more heterozygotes than homozygous grays, but some grays should still be present. Our data shows at least one gray is still around. Maybe migration did occur. I'm picking up weak colony life signals in an unexpected and previously unmapped location. Hold on, let me triangulate it. Hooray, we found them. Looks like a small contingent of the colony broke out on their own into this snowy cold terrain. In this new environment, what do you think will happen if we venture into the future? The dark scrub and light snow both provide good cover. I could see dual survival happening. Let's find out. Trigger a time jump to see if any changes occur. Well, would you look at that? The gray fur color must have been an advantage after all. The gray canids have proliferated most successfully and formed a new colony of their own in this new environment. Migration to new environments that favor different genotypes is one of the strongest drivers of speciation. While these canids don't represent a new species yet, they could in theory become one should the colony become isolated from their ancestral counterparts and undergo further adaptation. Speciation takes a solid million years and we're currently 16,000-ish years in the past, so maybe in the year 984,000 we'll have a whole new canid species to investigate. The incremental changes we've considered in the canid colony are the building blocks of evolution. Speciation can occur in many different ways. What is the difference between genetic drift and natural selection? That's right. These canids result from a change in the climate. Right now Earth is in an ice age, however, the climate will warm in the future. What do you think would happen when the climate changes? I could totally see selective pressure shifting to favor the ancestral allele again if the colony's habitat reverted to temperate forest. Such reversals of natural selection happen all the time, for example when a previously lost apex predator is reintroduced to an environment. Oh my, the clone I left with the dogs only has a short battery. I've enjoyed guiding your evolutionary exploration so much I completely forgot about it. I hope it hasn't died. Let's quickly go check that they're okay. Ah, lovely. It seems that these canids are experiencing zero external pressure right now. I'm so glad they didn't start barking at me again. Doesn't it seem wild that all terrestrial life came from one common ancestor? Such variety in only a few billion years. What part of our exploration interested you the most? I guess for a human, a million years is a practically unimaginable time frame. People had a hard time accepting evolutionary theory when it was very new. Some people still do. The fact that evolution happens so slowly that you can't see it happening was one big reason, among others. Thank goodness for fossils in the Galapagos archipelago. If you're unaware of the fantastic creatures there, explore Darwin's adventures in the islands and how they helped crystallize evolutionary theory. I think I just heard the doorbell. Funny, it sounded a lot like a dog whistle I tried out once. My assistant must be back. I hope you enjoyed your explorations today. Remember to keep an eye out in your own environment for natural and artificial selective pressures. Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.